Hello, everyone. Welcome back to my channel. Today we're going over this problem of control. So calibration curve for a mass balance with input mass and output voltage. The data represents the average from many cycles of increasing and decreasing mass. The equation for the best fit line or the dashed line is y equals 0.823 x minus 0.57. The table of calibration data is on the right. We want to use this figure for problem 12. So a mass balance is characterized by the calibration data in figure 6. Estimate the input uncertainty uh, in kg of an arbitrary measurement made using this calibration. So yes, the equation, yes. The mass balance is characterized by the calibration data in figure 6. Estimate the input uncertainty or measurement uncertainty in kg of an arbitrary measurement made using this calibration. Your uncertainty should consider the entire input range and should be valid for measurements made after the user arbitrarily adds or removes mass from the balance. So what is this asking us? In other words, this problem is asking us to compute the maximum nonlinearity and then convert the output uncertainty into input uncertainty and then use this to calculate the uncertainty. So basically, the problem statement states that the data represents the average of many cycles of increasing and decreasing mass. The associated repeatability error that was averaged out over many cycles is not quantified. Although it may be a bad assumption, we will assume this repeatability error is very small in comparison to other errors in the problem. So, uh, yes. So the input uncertainty is going to be related to the uh, maximum nonlinearity and the hysteresis, which is the slope of the graph. So basically, the maximum nonlinearity from the graph is going to be the maximum departure from the best fit line. Um, and it occurs at around an input of 4. As you can see from the graph, if we observe, maximum linearity means the point that deviates most from the best fit line, and it occurs at point equal 4. As you can see, this point is higher than all the rest. And at point equal 4, we can read from the diagram that the maximum nonlinearity is equal to basically, oh wait, hold on. Yes, it's equal to basically 1 point so one whoa, it's a lot. Yes, it's equal to 1.86 minus uh the y value from plugging in x equals 4 into this equation, which is minus 0.823 times 4 uh minus 0.57. And this value is equal to negative 0.86 volts. And this one is the maximum nonlinearity. Uh, let's call it maximum nonlinearity. And basically, um, we also want the static sensitivity from the best linear fit to convert output uncertainty into input uncertainty. So that will come from the hysteresis, which is the slope of this best fit line. So KO, which is the uh, static sensitivity, is going to be equal to 0 0.8 0.823. And basically the uncertainty in kg is going to be represented by the maximum nonlinearity over the static sensitivity, which is max n over ko, which is equal to negative 0. But actually the absolute value of that. So the absolute value of the maximum nonlinearity over the static sensitivity. So absolute value of negative 0.86 divided by 0.823. And this value is going to be equal to 1.04 kg. So we want to okay, yes, that part is finished. And we want to do part B. So we want to explain why it might be advantageous to require users to add the mass to an empty balance when making measurements. And this is because the effects of hysteresis could be reduced by fitting to only the data with increasing mass. As a result, it appears that uncertainty could be reduced to about half. Yes. So I hope this problem was helpful for you guys in gaining a better understanding of how to approach these kind of problems, and see you guys in the next video.